Fine. Next, we are seeing the what are the various detailing requirements of any reinforcement structure is considered. First thing is, as a simple bar we generally don't use. That is, a straight bar is used at a often very lower locations. So that is at less locations we use as straight bars. Often this rebar location, rebar detailing is governed with placing of some head hooks or the end anchorages that improves the anchorage bond, and also to have the different forms of reinforcement, that is in the form of stirrups or any links or any end anchorages like L bends or hooks or any cranking of the bars. All this will require some sort of bending of the rebars from the plain bar to a different shapes of configurations. In this criterion, we require bending of the bars. This bending of the bars will be done with the help of a mandrel. Mandrel is nothing but a support that is fixed to a fixed support, using which that as a support for the bending of the bar. We bend the reinforcement with some sort of levers that was there. Lever is the movement force applied for bending of the bar, and mandrel is the bar that is a supporting bar to form the required radius of the bar. Most of the Indian construction industry, especially in the small scale, the main problem that is coming is with the improper selection of the mandrel diameter. The IS code like IS your 2502 and also the SP34 and including the IS 456 2000 clearly shares that this bend radius should be within the specified caudal limits. Why? Because whenever we are bending of a bar, there is generally two type of stresses that is generated in the structural element. That is, in the concrete, there is an outward radial strain that is generated in this direction at this bend location. This is a highly stressed zone in the concrete, which is much more higher than the your compressive strength of the concrete. Sometimes, if the your bend radius is not within the permissible limits, that is the radial stresses that is generated in the concrete, we call it as a bearing stresses that is in the radial direction, will be higher than your permissible compressive strength also if the concrete is of lower grade. In the earlier cases of practice, we have M15 or M20 that having very lower bearing stress of 0.4 FCK, that is in the order of 4 to 5 Newton per mm square for the M15 to M20 Newton per mm square. Therefore, for the lower grades of steel, this radial bearing stress that is at the bend location will be critically a problem. Besides that, the change of tension direction in the radial pattern will induce a outward flexural tension that is at the bend location. That what we are seeing at this red portion here. This is the radial flexural tension cracking that is developed in the form of airline cracking, generally not visible. If it is beyond the your excessive one, it will clearly visible to the with naked eye also. This is also a critical stress plane if we are not adopting a proper mandrel diameter. The code clearly specifies that if the mandrel diameter adopted is 4 times the bar diameter, then there is no need to check the your bearing stresses that is at this junction. Otherwise, you have to definitely check the stresses of bearing stress at this junction of the concrete and also within the steel. Therefore, in most of the Indian standard practices, the main mistake that is coming is selection of this mantle diameter. Generally, the minimum mantle diameter is 4 times the bar diameter. We generally adopt a 2 times of bar diameter. The 12 mm bar is fixed to the wooden scantling or the log, and that is used for the bending of the rebars. That is a very crude and unacceptable practice that we should eliminate at the basic stage of the detailing also. That 4 times bar diameter at the mandrel is compulsory for the any bar bending is considered. And bend test is one of the tests as per the IS 1786 is required. What it gives is the qualitative information regarding the fraction capacity of this rebar after its bending of into hook or L bend. That is whether the bar is permitting without any development of tensile cracking at this junction. safely, that can be assessed with the help of this bend test that was suggested in the IS 1786. That is the code of practice for the steel reinforcement is considered. And just now we have discussed that this manual diameter should be with respect to the bar diameter what we are bending. That is for the 12 mm bars, it is 12 times to the 4. That is 48 mm is the manual diameter. For the, it is a stirrup 8 times of the 4, that is 32 mm. For different bar diameters bending, we have to use different manuals. Generally, what we do is for all the bars of 8, 10, or 12 mm, we use the same manual. That is a incorrect practice that should be avoided. And one more important parameter that is to be considered is the selection of a TMT bars. That is, in the modern days, we are selecting and using this TMT bars due to its market availability, and it's only the available bar in the market now. These TMT bar with lower diameters of less than 12 mm, say 8, 10, 12 mm bars, there is a possibility of this irregular formation of these two distinct constant materials. That is, a TMT bar is a composition of a outer tempered magnesite, that is generally 10 to 15% area is outer ring, and it is a ferrite pearlite core which is giving the your percentage elongation, and the outer core is giving the magnesite is giving the yield stress due to its hardness and tempering process, and the inner core should be a concentric with the outer magnesite phase. This concentric formation during the metallurgical phases and the steel manufacturing process is important to minimize this type of cracking that is at the bends. That is, in the case of 8 mm, 10 mm, and 12 mm bars, there is a possibility of metallurgical formation of this pearlite and ferrite and magnetite phase like this. There is a non-uniform formation of magnesite phase like this, what we are saying, that leads to cracking of the reinforcement at the bund. This is the very critical and a very important parameter that is to be looked into while detailing and our rebar fabrication is considered. Why? Because whenever there is a fracture is there, there is a initiation of the tension cracking at this junction. That initiates the fracture at this points, that is in the form of yielding at this stress concentration zone. This is a zone of stress concentration. Along with, due to the improper metallurgical formation of this pearlite magnesite phase and ferrite pearlite and magnesite phase, there is easily possibility of breaking of the steel rebar at a stress much lower than the your yield stress. Why? Because the soft core is that is the ferrite pearlite is meant for the your percentage elongation of the bar, not for the strength. The outer core is meant for the you are getting of the yield stress. Therefore, what is the yield stress that is getting from the outer tempered magnesite is already starts yielding due to the fracturing of the bar during its bending, and further it tries to propagate this crack into form of a cracking of a fracturing of this stirrup at this fracture zone. Therefore, the code is should also specify that this test is a compulsory test. That is, the ring test is a test that is there, but is not compulsory as per IS 1786. But the code should make it as a compulsory such that these types of failures can be avoided. That is, the formation of these irregular phases of metallurgical phases of tempered magnesite and pearlite can be eliminated or can be identified by conducting a ring test on a TMT bar. But the code is not made it mandatory. It is only a prescriptive manner. It is suggesting only the ring test, but code should make it as a ring test. Not only the codal practice, as a construction engineers, the designers, we have to test this in a simple way at our own site or at our own laboratory also. That is the importance of the ring test that is necessary for the bar bending of the this rebar detailing is concerned. Therefore, this rebar bending is an important role, is a prima facie requirement for any starting of fabrication of any good engineering practice is concerned. Now, this is a rebar detailing we are seeing. That is a clear-cut explanation of the various bars that is going from one location to another location. That is this is a raft foundation detailing with a raft sub like this, and we have a raft beam also there, and the column bars also there. This is the raft top steel, and this is the green one is a raft bottom steel, and these are the end bars of the we call it as a loops are the end anchors in the wrap slab, and the yellow one is nothing but wrap slab top and bottom steel, and this gray color or the black color shows the steel of the your column. What it clearly gives is the three-dimensional detailing will eliminate all the mistakes that is generally taking place, especially a complicated structures like wrap. This is one of the problem I recently come across in my own site, where I have given the excellent presentation in a two-dimensional manner for a with satisfying all the 2502 requirements and the SP34 requirements. In a two-dimensional plan, I have given as a reinforcement drawing, but the bar bender is unable to understand that complicated reinforcement drawing. And he made a mistake that this yellow bars that it should be has to pass within the beam bars. He has placed below the your column, beam, raft beam bottom. As a raft beam bottom, he has passed these bars. These bar has to pass this within the raft beam like this. In this figure of the 3D schematic, we can clearly see that can see that this how the raft sub steel is going inside of the your raft beam. That is a clear cut illustration is there, explanation is there. But once I had given this is a site in near the Bhimavaram Engineering College for one of the consultants I had given. The bar bender, even though I had given the a 100% correct two-dimensional drawing as per the Indian standards, the bar bender is unable to understand that engineering drawing, reinforcement drawing, and he put that bottom steel of the wrap slab that is below the wrap beam. That is a mistake. Suppose if I had given this much of clear-cut schematic drawing, I am in a better position of not removing all the rebars after its completion and placing in a correct direction. That type of errors can be eliminated. And also we can see how he had maintained the mandrel diameter, how perfectly he had formed the mandrel diameter. We can see for the stirrups also we can see how he had used the mandrel correct diameter. This is very important for the TMT bar point of view, and also for the your what we call the bend test requirements of the as per the 4 times of the bar for the IS 456 2000 or your the SP34 requirements is considered. Therefore, nowadays, whenever the client is interested or the client is able to pay the subsequent cost, it is better to have a rebar 3D detailing instead of a 2D detailing, which gives you a minimum mistakes and the minimum errors during the execution of the rebar fabrication in the site. Now we are seeing a schematic of a three-dimensional isometric view that is representing with a bridge PR. Generally, for the bridge drawings, there is a lot of amount of reinforcement is there when compared to building structures. That leads to so much of confusion. That leads to so much of mistakes also. This is a famous, we can say, a recent developments in the bridge detailing, where we are where we are detailing where we are detailing using the three-dimensional isometric waves. That is, the cyan color is indicating the pier cap, and the yellow one is your pier column main steel, and the brown one will be the stirrups. This is a typical way of these are the bearing detailing, and these are the spiral loops that was used for the taking of the bearing stresses below the pedestals. And recently we have seen one pier cap that is failed due to improper anchorage of the pier mainstay. That is lack of understanding of how the pier bars is to be anchored into the pier cap. That is the reason for that. That there is a due to the inadequate anchorage of these bars into the pier cap, the fixity requirements due to the insufficient development length of the pier main scale into the pier cap leads to a tension cracking at this interface, where the critical section for the bending moment is maximum, and it is a probable potential failure place. This steel rebar has not able to develop the full moment resisting capacity due to inadequate anchorage length of improper detailing, that leads to failure of this pier cap execution. Therefore, these these types of rebar detailing, not only for the buildings, for the bridges too, will be helpful for the easy and correct way of presentation of our steel reinforcement that is there in our structures. Now, this is a typical reinforcement detailing. Generally, we adopt in our design office, that is with a different color coding. That is, yeah, with the different color codings will give you different bars. That is, stirrups will give one color coding, the member size will be given one color coding, and the bottom bars will be given one coding, extra bars will be given one coding, and the bottom bars will be given one coding, top bars will be given one coding, and it depends upon the each bar will be given with a different color coding, and will be the printout that is in the form of hard copy, and the soft copy is also presented in the color full drawings and the colorful soft copies. What is the basic advantage of this detailing is, color detailing is, it easily identifies the bar location, bar numbers, and also the placement position and the direction of movement, that is the direction of placement of the reinforcement also can be better understood and illustrated using the colorful drawings. Generally, we adapt our design officers. This is the one of the standard good engineering practice. Generally, we have to cultivate for the elimination of the errors and also to have the correct detailing practices. This is a close-up view of the earlier drawing, that is in which we are coding the different bars with different parameters. Here we can see the top bar is coded with a green color, and the bottom is coated with a brown color, and this beam with a different length is coated is given with a cyan color, and the stirrups is given with some red color. What this clearly indicates or the illustrates is we can they easily identify the different rebar detailing and the rebar locations very easily without any confusion to the even to the layman also. That is the importance of the rebar detailing with the colorful presentation of the drawings, both in terms of the soft copies and the hard copies. Now we are seeing the detailing practices of various column members and also various footing members. That includes also slabs and the your beams also. We'll see different structural elements. What are the various detailing requirements of the codal practices provisions, and what general mistakes that is taking place, and also the explanation through some videographic presentation. That is very important. Now we are seeing the rebar detailing of a column. This is also unfortunately it's one of my slides, but there is some sort of mistake due to communication error, and this is a rebar detailing that was taken place at one side, where the column dimension at the lower floor is having a higher size when compared to the column dimension having at the upper floor is having a lower dimension. That is, there is a decrease in the bar size from one floor to the other floor after certain height. And for this, the correct way of detailing is generally not understood by so many designers also. That for the engineers, site engineers, there is again a entire mess is there. The basic codal requirements of these types of bars is, first requirement is this spraying should be not more than 1 in 6, and there should be a close spacing of the stirrups at this with the spacing not more than 150 mm, and these stirrups should have a special type of contact, like that is a mandatory for all the type of bars also, and there should not be any gaps like this. And these are the basic mistakes that took place. Besides that, the location of the decrement of the spraying of the column main bars is not at the top of the slab. That should be at the bottom of the slab where the member size is more, and it should be confined within the beam location. That is very important. Here, with the communication error, what they did is they made that spraying of the bars, that is the reduction of the column size above the top level. That is a basic mistake. That should be done at a level much below this slab top level. That should be confined within the beam concrete. The beam concrete will offer the adequate lateral resistance, and also the spraying is also should be there within the the beam location. We'll see you some video presentation of this for the clear-cut understanding. Sir, is it visible, sir?
Visible, sir.
Yes, sir.
Yeah. Please observe very carefully how the bond strip is placed in the beam column junction, not at the top of the slab.
Is it a video?
Yeah, it's a video, sir. Are you visible, sir?
No, sir. It is only showing.
One minute, sir. We will make the arrangement. 1 minute, sir.
It's not playing.
Yeah. It has to be played, right?
1 minute, sir.
We are seeing the stirrups placement. That should be not more than 150 mm at its staying location. That is the first criterion. The staying bar should be within the beam location. That is within the beam element. It should be confined. That beam, what is the outward stress, horizontal stress coming at the top of the ink? That should be taken care by the pivot that was placed at the top link, not at the bottom link. At the straight location at the top link, the outward component of the your sensor force will be taken care by the stirrups of the top link. That is here. That what is the blue one here? The straight top link stirrup will be taken care by the horizontal tension component by the coming from the main steel. In the earlier side, what we have seen is unfortunately the spraying was done at the top of the slab. Yes. Shall I go?
Go.
Sir, am I visible, sir, now?
Yes, sir. Yes, sir.
1 minute, sir. 1 minute.
Am I visible now, sir?
Yes, sir. Yes, sir.
Yeah, fine. And after that, we'll see the very important requirement of this rebar detailing of the column bars. That is generally we know that the manufacturing of, as per the Indian practice of the steel industry, we have a 39 to 40 feet is the length of the bar that is available. Definitely, we have to lap the bars at desired locations, and this selection of the location of the lapping is very important. Besides the lap length and also the number of bars that is to be lapped. These are the three important parameters. Generally, in most of the sites, we do the mistakes here. That is, whenever lapping is there, the lapping is incorrectly planned. That is in terms of its location and also its lap length also. But to some extent,
You see, I
3 times
I'm not able to.
diameter. Hello? Hello, sir. Am I audible, sir?
Yes, sir. Yes, sir.
The three mistakes generally we come across is in terms of the lap location, development length of the lap or lap length, and also the number of bars at each location that is to be lapped. These are the three mistakes generally we come across, and even this lap length the should be we have the equals to the development length in tensional compression. In the Bhuj earthquake in 2001, earlier we have a distinction between the lap lengths for the compression, it is different, and the tension, it is different. The failure after the Bhuj earthquake in 2001 is had given some sort of lessons to us in terms of the lap length that was provided as a compression has failed due to inadequacy in the lap length in the development of the required tensile force in the member. That leads to failure of the members. Therefore, nowadays, once we are adapting the seismic resistant designs, the lap length what we are considering should be with respect to the lap length of the tension only. The lap length in the compression generally 25% will be less when compared to the tension, but we, as a seismic resistant point of view, and also for the normal non-resistant seismic resistance of point of view, also don't adapt a lap length equals to lap length in compression. That won't save you much of cost you. But the damage it will do to the structure is much more enormous and leads to some kind of catastrophic failures also. Therefore, what is a lap length that should be considered as a lap length in tension only. And most of us, we are considering 51D, that is almost sufficient, or you are precise in having the execution under the design point of view, you can save the lap length also by properly designing based upon the bar diameter, the grade of steel, grade of concrete, and the type of steel also. Considering all the realistic parameters of the lap length requirements, you can design less than 51D also, or 51D is safe for M20 and FE4 and 5, that you can adapt for all the lap lengths. Generally, this mistake generally will not happen, but the main mistake will come from the lap length that should be in the tension only. That should be kept in mind, even though you are not considering as a seismic resistant design. Why? Because that gives you additional factor of safety, even though you are not designing as a non-seismic resistant design. It costs you not much, but it will save you your structure from its failure. And regarding the number of bars at each location, number of bars at each location, generally preferably 1/3 of the bars to be lapped at one location, and at the maximum not more than 50% of the bars to be lapped at this one lecture. In this you can clearly say that all the bars are lapping at the top of the slab. That is, the 6 bars are planned to be lapped at the one location. That is a very, very wrong practice. Why? Because whenever a lapping failure is there, that leads to failure of this entire junction due to lapping failure and the sectional failure of the member at this junction itself. Therefore, preferably 1/3, but to the maximum extent, not more than 50%. But prefer only 50%. Why? Because there is a difficulty in 1/3 lapping. That is, your zone of lapping also will be determined by the plastic hinge formations when we are considering the seismic resistant designs. That is, your lap location that just now we will discuss. That lap location is also important, not only the lap length and the lap location and the lap number of bars that is to be lapped at each location. 1/3 lapping requires a critical and planning and execution of at the site, but 50% also is a permissible one. You adopt a 50% that is more convenient based upon the field practice is considered. If you are stringent, it's better to have a 1/3 lapping at each location. When we are adopting the 50% of the lap, you have to consider what is the lap location. For the lap location, For the lap location, you have to consider what are the probable locations of the plastic hinges that is formed if it is a seismic resistant design. Based upon that, so plastic hinge locations are the locations where there is a plastic movement is there. That is an amplification of the movement beyond your yielding of the strain. And the movement under that, the member will try to become a plastic hinge that's similar to a mechanical hinge. It has the infinite rotation similar to a mechanical hinge. Therefore, the plastic hinge locations at this, you should not have the location of the splices. Plastic hinge locations for the seismic resistant designs will be at the top of the beam and also at the bottom of the column and top of the column and also at the side of the column and the side on the other side of the column. These are the four in the beam column junction. These are the four possible plastic hinge formation locations. At these locations, if it is a seismic resistant design, you should not form the lapping at these joints. But where it is to be formed, it is to be formed at 1/3 or at the middle of the section, and preferably it should be welded when it is a seismic resistant design. And when you are using a non-seismic resistant design, like in the previous cases, the ideal location is at the top of the your slab concrete. That is the location where the flexural yielding plane in the column is at the middle of the section. Suppose it's taking as a fixed end column as a boundary conditions. 0.5 L is the your effective length and midpoint is the your yielding point. Therefore, it's preferable to have a location of the last place at the end of the column and the top of the column. If it is not possible at the end, you prefer these locations for the spacing of the columns in the case of a non-resistant, non-seismic resistant designs. These are the probable locations where the lapping of the bars is to be suggested. That is also important. Once you are forming the lapping at these joints at the top of the slab of the column, the bottom of the beam of the column, that is the probable locations for the your plastic hinges for the seismic behavior of the structure. That leads to formation of plastic hinges and the easy failure of the lap joints at the case of a seismic resistant construction is considered. That is the seismic behavior is considered. Now we'll see some of the provisions regarding the pile cap and the footings also. Before going into that, we'll see some of the provisions with respect to the this footings. In the case of the footings, the generally 2 to 3 types of mistakes generally we come across. The bottom cover is generally 50 mm that we know. Generally, we don't do any mistake with respect to that. But the one main mistake we generally come across with the side cover that is there. The minimum side cover for any isolated footing is 75 mm, not 50 mm. Generally, it's 50 mm that is for the bottom. We try to adapt for the sides also. Why? Because it's higher cover for the sides and the lower cover the bottom is the permeability of the liquids which are harmful to the concrete is very important. We have 2 types of permeability. That is permeability that is passing from the bottom of the concrete or the footing, and also the permeability of the liquids that can be water or harmful chemicals like saline water or oxygen intake, whatever the harmful sulfates or chlorides, ion migration, whatever the harmful deteriorated materials ingress into the concrete body will be from the bottom, or it can be from the sides. The bottom, it's a vertical permeability. From the horizontal, it is a horizontal side, it's a horizontal permeability. We have to consider the permeability of the concrete both in terms of the in the vertical direction and also the horizontal direction. Similar to soil also, there is a distinction with respect to horizontal permeability and vertical permeability. We generally distinguish the soil permeability generally 10 to 1,000 times. It is much more higher for horizontal permeability when compared to vertical permeability. Similarly, also keeping in this variation in the permeability of the concrete in the vertical and horizontal direction. Now, IS 27 IS SP 34 also specifying that the side cover is 75, not that 50 mm. That is also there in the code illustration of the SP34. You refer to that after this completion of the webinar. Why? Because the horizontal permeability is higher. Therefore, the chance of migration of this the harmful ingredients of this chlorodion induced that is diffused through water, or the sulfate that is insoluble through water, will be much more in the horizontal direction. Therefore, code is prescribing higher value of 75 on the side direction. And also the L requirement, that is the L bend requirement, generally we do some sort of mistake. Generally, the L bend requirement can be put in all the sides. That is not required generally. That is a wastage of steel. Why? Because this L bend requirement is a function of the development requirement after the your face of the column. That is a critical section for the flexural bending moment. Suppose this is a cantilever bending moment of this footing edge that has a critical section like this, spreading from this edge to this edge in the form of vertical plane, and beyond that it is having the fixed zone for the anchorage of the steel that was there. That is suppose take this bar is into consideration. This is a cantilever flexural bending moment that is in the upward direction with the tension plane at the bottom. That has a anchorage length beyond this critical section for the bending moment, that is from this 40 mm from this stirrup of this column, and starting from this should have a development length. If the development length, the straight length is not sufficient, then only we have to bend this into L-shaped bend. Otherwise, it is not required. Simple straight bar is required. But as a general rule of thumb, we will put for all the footings, L bend is compulsory. This L bend is compulsory when there is a small size footings like 1 meter by 1 meter or 1.2 by 1.2 meters. For the small size footings, being a lower production length, you have a requirement of development length of 51 days, which necessitates this L bend requirement that is necessary for the footing requirement is also. This is putting L bend for all the footing scale, main scale is almost sometimes of wastage of money. That is generally we are adapting as a with a unwanted practice that is generally taking place in the field. And one more thing is whenever we are doing a seismic resistant designs, this steel that was there in the footing embedment, that is the column rebars that was there. What is the columns rebars as a starter bars that is going on from the top of the second mat of stagnant bars of the footing steel? Generally, these will be from the top of the footing to the this edge of the L starter bar. This should be development length in the compression as specified in the code. But our modern practice is consider this not as a development length in compression, consider it as a development length in tension. Why? Because we'll see in the following video graph also. The code is specifying that this is LD in compression, but you consider LD in the tension zone only. Why? Because there is development of pull-out tension that is in the footing due to the seismic lateral forces. Therefore, this development length requirement in the compression should not be considered, and it should be considered a development into the tension from the top of the footing to the end. And this generally code is suggesting minimum 300. This 300 mm is should be more than 300 mm also. That should be checked with respect to LD in tension from this edge to top of the footing in LD in tension. Not minimum 300. Minimum is 300 mm, not 300 mm. That should be identified and should be justified. And one more thing that is a requirement of the footing is whenever you are designing a seismic resistant designs, there is a possibility of the plastic hinge within that footing concrete also. That is, what is the footing depth? Say my footing depth is 500 or 550 mm. Within the 550 mm also, there is a possibility of plastic hinge. Generally, we generally don't think of the plastic hinge formation within the footing. Therefore, what the requirement is, you have to form a spiral reinforcement or closed spaces reinforcement within the concrete from this edge to the top of the footing. Suppose say my top of the footing is here, and from this edge to this top edge, if it is a circular column, you have to form a spiral loop. And also, if it is a rectangular column or square column, you have to place a closely spaced stirrups on space not more than 150 mm. Why? Because there is a possibility of plastic hinge. This plastic hinge can be taken care of by the stirrups that was additional stirrups that was provided in the footing. That is, not only the column and confinement at the beam column junctions, the confinement of the column in the footing is also important for the seismic resistant design point of view. That's why I want to highlight. I will show you 2 slides. After that, we'll have a presentation. The next this one. Yeah, now we are seeing a typical detailing requirements for the pile cap requirements is there. The general mistake generally takes place in the case of piles is the clear cover to the pile main reinforcement is 50 mm. And generally the mistakes has taken place in this manner. The minimum embedment length as per the IS 456-2000 is 50 mm. As per the ACI 318, that is the US code, it is 75 mm. This embedment of projection into the pile cap is necessary to have the fixity of the pile cap into the pile. That is important. Whenever the movements of the pile is higher, acting on the pile or column is higher, you prefer a 75 mm embedment of the pile. That gives a better anchorage of the pile embedment into the pile cap. That gives a better fixity to this junction of this pile cap and your pile. And the cover 50 mm should be above this pile embedment of 50 or 75 mm above this pile top. That is, this is the pile cutoff level. Above that, you have to maintain the 50 mm. Generally, most of the sites, the top reinforcement of the pile cap will put on the top of this cutoff level. That is the top of the chipped level of the pile. That is the incorrect practice. Why? Because there is a stress transmission that is taken from this top edge of the pile only, not from this edge. This will be truncated 45 degrees and will be propagated up to the mid depth of the pile cap. This 50 mm cover is from the top of the pile cap. That is from the bottom or the top of the PCC and at the bottom of the pile cap. Your minimum cover is it can be 100 mm. If we are adapting this as a 75 mm, that is a 125 mm is the cover for the main steel. About that, that's. And one more mistake is the side cover is 75 mm, similar to putting not 50 mm in the case of piles also. The reason behind just now I have explained. And one more thing that is generally done a mistake is the embedment length of the pile into the pile cap. That is, here I have not shown the pile reinforcement into the pile cap. This is the actual typical illustration in which the length of the pile main scale should be embedded up to a development length, so that there should be a perfect fixed complete restraint of the fixed end joint. That is the total length here plus this 350 mm here I am showing. This should be equals to development length in tension. Some codes, the foreign code said that this should be minimum 300 and minimum 300. For the IS point of view, there is no such restriction. But this should be like a total length from here, that is from the top of the cutoff level of the pile to this element top should be up to development length, so that the full tension is developed in the pile main steel. Thereby, there is any release of movement at this junction. Once you are providing an insufficient length, that leads to some sort of formation of release of the movement in terms of release in the steel movement due to inadequate anchorage length. That is one of the mistakes generally we do. And also one more mistake generally come across is the L bend that is taking place here. This should be from the critical section, that is from the critical section, generally from the suppose if this is taking as a concentrated load transmitting in this direction, and this is the probable plane for the critical section for the bending moment, and beyond that it is a anchorage. This anchorage length beyond this critical section should be equals to the development length, and that should be maintained. If it is sufficient up to, we can curtail up to this length, or otherwise we have to extend. Here it is a 450 mm I have shown, and up to 450 mm what is the development length requirement LD from the critical section to this is to be maintained. If the pile cap is of shallow depth, in such a case you have to bend the steel like this also. Not only this L bend, you have to U bend similar to end hook for this bottom steel reinforcement. And also one more mistake generally takes place is the bursting steel that was taking place or putting in the pile cap. This is the bursting steel. Generally, we put it at the rate of 0.2% of the pile cap area. Pile cap AST, that is the main steel, bottom main steel. This 0.2% AST is to take care of the bursting tension that is coming in the radial direction. This bursting style should be is a all-round ring, that is a not as a simple two types of links due to the inadequate availability of bar length. It should be continuous loop, and the end should be have the development length of passing one bar over the other. That is, if it is a pile cap, rectangle pile cap, that should be all-round periphery. At the end, the lapping of LD should be there. And also, if the continuous bar is not there, you have to weld that joint. Welded joint should be used. That is a continuous stirrup with a end hook of not 75 or 75 mm or 10D or 6D. It is a LD of the entire end hook length should be there, and it's a continuous not as a 2 pieces or 3 pieces or cut bars that is should be used. If it is cut bars, you have to again lap length should be welded for the each. That is, it is the form of continuous loop that should be used to take care of the bursting tension that is coming on the pile cap. Otherwise, what is the amount of 0.2% or 0.3% you are providing? That will be no use of providing that amount of steel. Now we are seeing some of the provisions regarding the stirrups requirement. This stirrup, this is a typical photograph of failure of a building structure, RCC building structure, due to inadequate and improper and incorrect stirrups that was used in the Turkey earthquake. That is, you can see how the stirrups are missing with this highly seismic zone activity of Turkey. You can see how the main bars are exposing, and you can also see how low number of stirrups are there. This is a typical photograph from the Turkey earthquake is there. Sir, play jayega. 2 minutes, 5 minutes of questions.
The building corner is subjected to a closing moment, the top rebar is tensioned. When subjected to an opening moment, the lower rebar is under tension. 2. There must be plenty of well-anchored stirrups in columns and beams to resist high diagonal tensile stresses and cracks and ensure ductile behavior. Eliminating one stirrup can reduce the column capacity by 50%. 3. Strong columns, weak beams. In the case of an extreme earthquake where failure is unavoidable, we prefer the beam to fail. Column failure could lead to complete building failure. Three important rules for designing RC earthquake-resistant buildings. 1. Lower beam rebars must be anchored the same as the top ones. When a building corner is subjected to a closing moment, the top rebar is tensioned. When subjected to an opening moment, the lower rebar is under tension. 2. There must be plenty of well-anchored stirrups in columns and beams to resist high diagonal tensile stresses and cracks and ensure ductile behavior. Eliminating one stirrup can reduce the column capacity by 50%. 3. Strong columns, weak beams. In the case of an extreme earthquake where failure is unavoidable, we prefer the beam to fail. Column failure could lead to complete building failure.
Sir, sir, my screen is sharing. Yeah.
Yes, sir.
Now we are seeing the detailing requirements with respect to the stirrup of the column. It is very, very important. Why? Because in the case of seismic resistant designs, not only for the seismic resistant designs, for the gravity load designs also, the column failure should not be takes place. Takes place. Why? Because the column failure always be a catastrophic failure and also a brittle failure, which will not give you any impending warning before failure is taking place. And the cascading effect is also there, which leads to the failure of the one column leads to failure of surrounding and the entire columns also. And also the moment distribution is also not there in the case of columns. All these factors will lead to a catastrophic failure when the failure is with respect to a column failure. Keeping all these points into consideration, in the case of a seismic resistant designs, not only for the seismic resistant designs, for the gravity load designs also, the column failure should not occur. Generally, in the case of a seismic behavior of the columns, the stirrup behavior, the concrete behavior, including the main steel behavior, is plays an important role. Among these, the stirrup behavior is plays an important role. Why? Because the code is also gives some sort of prescriptive way of understanding of the stirrup arrangement, not as a complete understanding of the subject also. But we require a complete understanding of the behavior of the lateral ties of the columns, so that there should not be any failure of the lateral ties. Thereby, there will not be any failure of the main steel that is there. And the possibility of failure of the column stirrups in the case of column is more when compared to other structural main components of the main steel and the concrete that is there. Therefore, the failure and the behavior of the stirrups is to be looked into very carefully. That is very important. Just now we'll discuss that points. And before that, the in the case of a seismic resistant designs, the code is emphasizing various codal provisions as per the seismic ductile detailing point of view, also for the non-ductile detailing point of view. For the ductile detailing point of view, we have the IS code of IS 13920. The ductile designing and the your design detailing provision should conform to IS 1392, in addition to IS 1893 and IS 456 2000 provisions. Therefore, in this, we have a requirement of this. In the case of a stirrup, the end anchorage should be a 10 times of the bar diameter, subjected to a minimum of 75. This is also important. And again, there are two other clauses. Generally, we stressed about the end should be 135 degrees. That is bent into the core concrete. That thereby the core concrete is a more confined concrete. Within the core concrete, the end hooks of 135 degrees will be confined with the compression stresses that was in the core confinement. Therefore, this should be 135 degrees, not as if this 90 degrees bend as 45 degrees bend. It should be 135 degrees hook that is embedded into the core concrete, with a embedment length of 10 times of the bar diameter, subjected to a minimum of 75 mm. That is also important. Why? Because in the once we look at into the 456 2000 class, the minimum bar diameter is 6 mm, and earlier 78 version it is 5 mm only. Now it is 6 mm, and once we take as 10 times of the 6 wells, that is comes to be 60 mm. 60 mm is not sufficient. 75 mm is to be considered as also criterion. Therefore, 75 mm is the minimum value, and subject to a condition of 10 mm is the bar diameter. And again 135 degrees. In addition to that, we have one more class, that is the bend radius, that just now we have discussed at the starting of this webinar. That is 4 times of the end this inside radius of the bar that should be maintained. That is 4 times mantle diameter must be maintained, so that the ends will not be stressed to a higher stresses or the possibility of to eliminate of this cracking zones at the bending zones. Therefore, for the mantle requirement, 10 times of the underhook length are subject to minimum of 75 mm, and also you have the 135 degrees hook that is well anchored into the core concrete, and that is also necessary. And the other provisions are similar to your general codal requirements. That is, whenever you are the spacing between the two outer bars is going more than 300 mm, this outer tie is not effective. We have to provide an inside a link also, that is in the form of this. This should be actually not as this 45 degrees tie. It should be in the form of hand hook. This is one of the mistakes generally takes place on the site. Due to difficulty of in situ the bar bender of bending once again at the site of erection, after placing of the link, he has to bend this again 45 degrees bend at the site at this point. Then they will try to eliminate this laborious process. They will put this 45 degrees bends only, but it should be 180 degrees one. Like complete hook should be there. Otherwise, there will not be any confinement. For the hooks, it should be 180 degrees hook, similar to this. This should be bent after placing into the in situ position of the main bar. That is also important. and these are the provisions that is for the effective confinement of the outer lateral tie, that is in terms of the more when the spacing between the outer bars is more than 300 mm. And we'll see one videographic explanation of the behavior of the stirrups under the seismic loading. Under the two conditions we'll see. This is the typical behavior of the Kobe earthquake building that was simulated in a shake table test at the Japan's largest shake table facility available in the world. That was simulated after the Kobe earthquake. How the column is behaving with respect to the failure mode under the seismic loading is considered. Here we have to understand two different types of buildings, failures of the columns in terms of the stirrups is considered. First of all, we observe the failure of the column in terms of the crushing of the column, and also the buckling of the main steel, and also we'll see the stirrup failure as a one mode, that is the compression mode of failure of the column we'll see, and also after that we'll see the failure of the column, beam column end joint for the plastic movement equation, that is the moment under the plastic movement, how the beam column is failing, we'll see as a one point of view. That is the column behavior we are studying in terms of as a compression failure as a one mode, and as a formation of plastic movement at the beam column end as a one mode of failure. These two modes are important, and in these two modes also the interaction of the concrete with the steel with the lateral ties will also study with this videograph. Now we are seeing the compression mode of the column. In which the beam is not rotating, only the column is undergoing sustained higher axial loads, that is due to the increasing column loads under the effect of the lateral loading. That is the higher axial loads due to the lateral loading effect. This is the failure column mode we are seeing. That is the crushing of the outer shell concrete. After that, the stresses are transferred to the core concrete. After that, the stresses are transferred to the your main parts. And again, the main parts will be subjected to a higher compressive load. Higher compressive load. The load will be subjected to higher load. The movement classification section at the beam column junction. The action of the movement have a anti-clockwise opening movement. That is, the joint itself will be subject to rotation in relation to the structural elements of beam and column. Is also classification section of beam column. Sir, am I audible, sir?
Yes, sir, you are audible, sir.
Fine. Yes, sir. Yeah. Earlier we have seen the video graphic presentation of the failure of the column that is interacting with the shear as a shear wall also, and this is a that is pertinent to a Kobe earthquake simulation, and this is the typical failure of the column under the bridge earthquake that took place in the year 2001, and we have seen that the two modes of failure. One is in the form of a compression failure in the column, and the second one is the form of a plastification or the plastic movement failure of the beam column joint. That is two modes of failure we'll discuss now. In this, the mode 1 failure, that is in the form of a axial forces. These axial forces will come in the form of a due to the gravity loading. In addition to that, the lateral forces, that is acting as a distribution of the interstory shear of the base shear in proportion to the lateral stiffness, will be subjected to a lateral deformation of the frame that will induce the push-pull action of the columns. That is the towards the seismic loading direction, the columns will be subjected to a much lesser load. It can be a tension also, or on the opposite side of the seismic excited acting forces, it will be subjected to a gravity loads, plus in addition to that a higher axial forces due to the seismic loading. That is it is subjected to a higher compressive loads when compared to a gravity loading. Under this increased axial forces, the mode of failure can be increasing the capacity of the member beyond its axial loaded capacity, in which the behavior of the column will be like this. Initially, the concrete will be stressed to a higher level, that is more than your 0.4 FCCal, 0.446. Okay, we can say it's up to the more than crushing value also. The outer shell of the concrete will start to crush itself, and there is after the crushing of the shell concrete, the redistribution of the stresses takes place from the outer shell to the inner core concrete. Now the load transfer, the stress transfer is from the outer shell concrete to the inner core concrete, and the inner core is trying to distribute and take the load that was lost by the shell concrete. And due to this, the increased stress level of the core concrete is subjected to higher compressive stress, and the concrete is now trying to crush itself under the increased axial compressive stress. Now, after the crushing of the concrete is taking place, is in the brittle model, the loss of the shell concrete compressive strength carrying capacity B is to be redistributed and should be compensated by the core concrete. Plus, there is an additional burden that is on the longitudinal main steel that was there. This additional longitudinal main steel is also subjected to increased compressive loads than what we had that was there in the gravity loads. That under this lateral loads, the ties that was there, lateral ties that is there, is subject to higher hoop stresses. That is, in the radial direction, the hoop stress will be generated like a bursting tension that is within the stirrups. That tension is to be resisted by your effective binding of the confinement of the lateral ties. That is, the lateral ties here is in the form of a pure tension member subjected to direct tension that should be effectively resistant as a continuous loop, not as an open loop. Suppose if the stirrup is opened like this, that the effectiveness of the lateral ties will be lost, and the column is main bars will be subjected to some bending forces. Why? Because earlier you have this treating as the main longitudinal bar as a main compression member. It has effective length between these two stirrups. Now your effective length becomes the spacing between the two adjoining stirrups into loss of this stirrup. Therefore, now we have the 2 times of the your effective length factor. Therefore, under this increases tenderness ratio, almost your capacity of the bar will be reduced by 4 times. Therefore, you have a buckling of the main bars that is taking place like this. That is, once you lost this stirrup cap pull up, like the bursting tension or hoop tension, and the increased axial loads of the crushing concrete and also the longitudinal bar, you have a problem of this buckling of the main steel that was there, that leads to again the initiation of the secondary effect of shear cracks and all that. in addition to the sectional cracking or the compressive failure also. This is a clear shear cracking combined with a crushing also is there. This mode of failure is possible with the inadequate lateral ties that was used in this. That is a 6 mm bars with nominal stirrups we are saying is this leads to entire mess in this case. And one more mode of failure that is there with respect to the stirrups is a development of diagonal tension in the stirrup similar to ordinary stirrups under the gravity loadings. In the case of gravity loadings, we see that tension cracks will be like this, making an angle of 45 degrees. And these tension cracks under the opening and closing movement will change its direction. That is, from this direction, inclination can propagate in this direction. Similar to a ordinary beam, which is subject to gravity loading, where the stirrups are effectively resist the transverse shear under the action of the compressive strength of the concrete, plus the double action of the stirrup that was there. The double action is nothing but similar to cutting up into two pieces, like with the scissors. This shear will cut your two-legged or four-legged stirrup that was there. It is a double action. That is the shear capacity of the two-legged stirrups that was there. For the seismic resistance point of view, we generally not consider the cranked bars. Therefore, the double action of the stirrups is come to play. Why this diagonal tension is developing is the closing movement or the opening movement that is acting. That is the movement acting on the beam. In the case of a seismic loading, is will be in the either clockwise direction or the counterclockwise direction due to closing movement or opening movement generation in the beam column joints. That is responsible for this joint rotation in addition to the structural elements of beam column rotations. That leads to this development of this diagonal tension cracking in your beams and columns also. That should be effectively resisted similar to a gravity load shear that was there. That is what we call as a diagonal tension cracking. This diagonal tension cracking is the second mode of lateral load behavior that is there. That should be, for this also, you have to confine this cellular province of 10 times what diameter or 135 degrees or 4 times the radius, and also the minimum 75 end of length. That's all this criteria is necessary in order to keep and to effectively stress that lateral tie that is in place, and also it should be effectively stressed to this. Here, one of the construction mistake that takes place is there is a gap that we are seeing in the lateral ties. This gap should not be placed after fabrication. Why? Because as just now we see how the main bars is buckling under the increased axial loads under the seismic effect. That even this lack of lateral confinement is there from the lateral tie, that simply buckle into the lateral direction. That is no effective lateral restraint from the stirrup, and it is try to easily buckle in the lateral direction. This type of gap should not be there after placing of the stirrup. That is also important in the case of a seismic resistant designs is considered. And also, it is preferable to have a closer spacing of the vertical ties when compared to a largest vertical tie spacing. And that is also one of the requirements we have. And we can see how the short bar lengths, like this is almost like without any end anchorage. Even 135 degrees hook is not there. It is not 75 mm. It is not 10 times of the bar diameter. Even it is for the normal gravity load casing also, the minimum requirement of the end hook is 6 times of the bar diameter. If it's a 135 degrees, I think it's 8 times bar diameter, 6 times bar. 6 times of the bar diameter is not there, even for the gravity loading also. The main bars will fail under the gravity loading also if the stirrups are like this. There is a lot of, we can say, there's a lot of greediness or the stringentness to the client and the designers, we can say, to the fabricators also. Providing these types of stirrups is almost useless. And also these types of should not be there after the fabrication of the stirrups that was there. And almost these diamond rings, they should be also be bent like this, like this. This is almost like a 45 degrees bend. 90 degrees bend. This 90 degrees bend is also not permitted. It should be 135 degrees bend at the both ends. That is, it should be confined within the port concrete that was there. That is one of the drawback that is we are saying in the is a mistake with respect to the slide is concerned. With 1 or 2 slides, I will close this. And this is a case where the binding wire that is not used of improper number, and also the tying is also not the correct. here generally we use 2 numbers of binding wires for twisting. Even one bar which was failed during the twisting, the second bar will be in position to keep the 2 bars in the position. And also the gap that was there for this column main steel should not be there. There should be effective restraint, just now we have discussed, from the main bar to the lateral tie. And the minimum 2 bars binding wires should be used. And the twisting also not correct. Why? Because there is a practice called in local language called as Enu Melta or logarithmic spiral. Scientifically, it's a logarithmic spiral. That logarithmic spiral will minimize what is the tension that is developed in your binding wire. That is a technique of binding this Enu Melta in the local language, or the logarithmic spiral. That concept is also we are using for the Gabion baskets and also for the various types of engineering mooring of ships and etc. What is the basic advantage of this Enu Melta, the logarithmic spiral twisting, is the tension developed in the binding wire will be almost very minimum. With elephants also can be easily tied with this of twisting knot of logarithmic spiral. That is generally we use. Once we use this open type of non-standard practices, that leads to development of lot of tension in the binding wire. Generally, it's 0.9 to 1 mm or 1.2 mm binding wire is there, soft material of any wire. That is not effective. That will cut during the twisting itself. The correct twisting is also important. 2 numbers is also important. Minimum diameter 0.9 or 1 meter or 1.2 mm is important. And also the lack of this should be closely tied during the tying process. That is, there should not be any gap. Recently, we are seeing some of the videograph presentations also site fabrication of the bar bending. That is also effective for the small 6 mm diameter bars. Say the site itself they are bending with some simple lever. That is gives a better efficiency with respect to giving no gaps to the steel reinforcement with the stirrups. That is also a good construction practice. And these are the typical mistakes generally we come across with the usage of PVC conduits. These PVC conduits are a distinct material that we use in the concrete placed above the steel reinforcement, but that is below the neutral axis. Being at the supports, we have the double reinforced section. Your neutral axis is almost at the mid surface. Your entire pipe, these PVC pipe is within the tension zone only. That leads to development of tension crack after the hardening and shrinkage of the steel due to the thermal expansion stresses. These are very dangerous. Whenever we are using this, it is preferable to place with minimum pipes or no pipes in the slab itself. If we are interested in place, the minimum number of pipes to be placed and should be jumped from a beam and to the slab with 1 pipe only, not as a continuous network of radial pattern or a continuous pattern. This continuous pattern will give you a lot of tension cracking. Why? Because it will intercept your yield line patterns. Yield line patterns will generally form at the ultimate loads, not at the working loads. But what we are working is under the service loads, it's the working load deflections and the working load bending loads. But there is a possibility of the yield lines under the working loads only. The yield lines is what we call as Johansson's yield yield lines. That is forming under the your working loads. That is because of these weak zones, that is the stress concentration, the shrinkage and the thermal cracking that is preformed and pre-located pipes that was there. That leads to subsequent deteriorated problems of water seepage and also the ingress of various cracks of ingress of sources for the chloride ion, sulfate ion, oxygen, moisture. What are the concrete determinant effect environmental factors are there? These are the potential sources for the ingress into these cracks. Whenever you want to have this electrical pipe, it's better to have the chicken mesh wrapping or the modern day easily available this type of readily available glass fibers and the steel fibers are available in the market. You can simply cut to the required length and fix it with the binding wire. Thereby, the outer surface has a better grip with your concrete that was poured. And also, previously we are using the black alkaline pipes that will have better surface roughness at the outer surface, that will have better bonding or gripping with respect to the concrete. And the PVC, you are inevitable, you at least make some sort of surface roughness over this outer surface of the PVC pipes and wrap with some glass fiber or the chicken mesh or this type of steel fibers, thereby and tightly tie with this binding wires so that there will be proper gripping of the concrete over your PVC conduit. Thereby, there will not be any cracking of the hardening or thermal cracking, or due to the stress concentration, or it can be due to your structural loading concrete due to the development of principal tensile planes that was there. Why? Because it's a stress concentration zone. Easily the yield lines will form at the loads itself. And you can see one more beauty here, that is continuous network of the electrical conduits. Then the continuous network should not be there. Whenever you are providing continuous network, the yield line form like this. And also more number of pipes here also. And also they had formed the pipes at the native bending moment zones of the beam, where the bending moments are formed and the tension zone is at the top. The beam will also have the some cracking with respect to the slab also. This is a wrong practice. And also this is a minute thing, but a very important thing. Why? Because in the case of a concrete, the compatibility of the strains is important. That is, what is the tensile, the strain the concrete should be equal to the strain the stress. That is a base composite material requirement, not only for the RCC. Any composite you take it as a FRP or any strain compatibility is important. Once you lost that strain compatibility equation, that is the slip condition, your function of the reinforcement is lost. That is, the two materials will behave as a two distinct materials. Therefore, strain compatibility in terms of the no slip or no loss condition should exist. For this, you require the better gripping of the concrete or the steel reinforcement. For that, we are using the modern days TMT bars, which has a much more higher legs when compared to the previous TMT bars also. Some manufacturers are manufacturing with extra ribs also for better gripping. And also this gripping with respect to the adhesion between the chemical and mechanical bonding between the concrete and the steel plays an important role in transmitting the stresses from the tensile stresses from the concrete to steel. The tensile stresses is a primarily will come from the concrete, and it will be transferred to the stress through proper bonding, that is the strain compatibility. This strain compatibility will be greatly affected by the what is the G-shuttering oil we are applying it for the slab centering. And once you are applying some muddy oils like these like used oils of the automobile industry, that will have a lot of sticky and also will not leave you, and it will minimize your bonding between the concrete and the steel. And this oil should be applied before placing of the slab steel about the centering the sheets, and after the placing of this beam steel. That is, whatever the oil you are applying, that should not have any contact with the steel that was used for the reinforcement fabrication point of view. In modern days, we have the de-shuttering oils are there, chemically stable compounds. These are preferable to use, but you have the economy is a point that you should not touch this oil applied to the steel reinforcement. Generally, the steel that was placed for the slab casting will be dragged over this applied oil. That should not be there. The steel should be placed over this applied oil after some sort of drying and all that. Thereby, there should not be any debonding effects between the concrete and the steel. And one more thing requirement is the regarding the TMT bars I want to highlight is the earlier bearing stresses was developed with respect to the code is for the you were considering it as a mild steel bar, which is a 2 times mantle diameter. For the twisted bars, it is a 4 times bar diameter. Keeping in view of the anticipated non-uniform formation of the outer the magneticite and the inner ferrite wear-like phase, the non-uniformity, especially for the small diameter bars of 8, 10 mm, 12 mm. Mostly in the case of slabs, we use 8 mm. Also for the steppers, we use 8 mm. It is a practice we have, and these bars will generally have a much more problem with this ring test of the irregular formation of the non-uniform concentric formation of this metallurgical phases. In such a case, the earlier code specifications of 4 times of the bar diameter for the twisted bars is maybe sufficient or not. Is to be judged through proper research. The Indian standard also has to put some research on this. Why? Because it's a very important role for the safety of the structure. Even the quantum of the steel is sufficient and have much more than the required values or the required amount. The improper placement of the steel or the inadequate anchorage length will lead to failure in the form of a pull-out failure or having a non-development of proper tension in the bar. This leads to catastrophic failures also. What I want to highlight is today's is the part 1 presentation. Part 2 is there. In the part 2, we'll see some of the detailing practices with respect to the slab and the beam, maybe probably 2 months or 3 months after this, that the part 2 is there with the permission of Mr. Zaragado and other members of the MC members of the Kakinada Center. In this, we'll see the presentation with respect to the slabs and the beams also we'll see, and some other miscellaneous elements also we'll discuss in the part 2. This ends my today's presentation. I would like to thank all the managing committee members, especially Badu Sundararaja and Durga Prasad Garu for giving me this opportunity. Thank you, one and all.
Thank you, sir. Thank you for your wonderful and thank you, Narasimharao garu, for your wonderful lecture. Very practical oriented presentation. Hope the same will be continued in the part 2 also. It's like our Bahubali 1 and Bahubali 2 part 2 will continue. Now I request the participant to ask their questions.
Sir, can you give me 1 minute time, sir?
Sure, sir. Sure. Okay, sir.
Yeah.
Oh.
Sure.
Now the participants can raise their queries.
There are 3 questions in the chat box, sir.
Yes, sir.
Yes, sir.
We'll answer the first.
Akul Rajesh posted a question. What are the recent softwares using for modeling?
Yeah. Not only the recent one, it's from the 80s itself. We have the availability of the software is there. ETABS, we have the world famous using the software that is only going with most of the expert structural engineers in the world. The basic advantage with the ETABS is we can model the advanced modeling like plastic hinge modeling with fiber modeling, and also that features are not there in the STAT itself. But the pride with respect to the status, it was developed by the Indian engineers. SAP and the ETABS are supposed to be treated as almost pioneers in the world. Recent advancements is with the fiber hinge modeling. That is the best softwares we have. Like other softwares we have, like Midas is there. We have Decaplat is there. STAT is a centralized and most used software in the world. ETAPS is there. SAP is there, and we have Robot is there. We have
Tekla structures.
Tekla structures is there. All these softwares are meant for the designing and detailing also. The main advantage with the current modeling of the, especially for the seismic resistant designs is considered is the ETAPS, in which we have this fiber hinge modeling is there. That is very, very advanced softwares, and also we have to look at into the how the non-linear material modeling is considered in the analysis. In the software itself is considered. Generally, mostly for the advanced design of structures, ETAPS is the popular one. STAT is also a very good software.
One more question. One question posted by Shivaprasad sir. 135 degrees required for guardrail handrail beam on bridges.
Shall you repeat, sir? Pardon?
Yes, sir. He is required 135 degrees
Hmm.
for guardrail beam, handrail beam on bridges.
Yeah, anything is requirement of the, in terms of the whether you are going with the type of design. Once you are going with the seismic resistant design, it's a compulsory, no doubt at all. For the non-seismic resistant designs also, code is also specifying 135 degrees for the stirrups, even though it's a non-seismic resistant design. Why? Because you have to confine the steel in the compression zone. That is a basic concept. That is, what is the concept of RCC design? First, we have to understand. In the case of a steel reinforcement, unless and until it is properly anchored in a sufficient passive zone, then only there is a development of the tension that was there. Suppose I require 3 bars is to be reinforced in a beam member or a knee member. This 3 bars is to be well anchored into the anchorage zone, so that what is the quantum of tensile stress that is to be generated due to loading will be generated only after have the sufficient anchorage only. Maybe it can be a static loading or a dynamic loading. Once it is failed in the this anchorage grip length, simply it will come as in the form of pull-out failure. There are 2 modes of failure. One is the form of pull-out failure. Second one is in the form of yielding of the steel, being a ductile material. The 2 modes of failure is possible. That is true with the fibrous materials also, like discrete fibers also. And these primary requirement is as necessity of anchorage of the reinforcement in the passive zones. That 135 degrees for the ports is also specifying prior to the seismic resistant designs for the stirrups also. For the bridges also the same criteria. Once we are providing the 135 degrees, but earlier there is a provision for this stirrup placement, that is in terms of the you can provide in the form of a 90 degrees bend or 45 degrees bend or 135 degrees hook for the stirrups of the beams, not for the columns. Columns, I think 135 degrees is compulsory even for the static loading. For the beams, you have the provision of but what makes its difference is, once you are putting for every 45 degrees, you have to consider the 44 times bar diameter. That is the anchorage length. That is 45 degrees you are providing. You have to provide a more hand length. For the 90 degrees, you have provided 6 times. For the 135 degrees, you have to provide 6 times the bar length. I think 8 times the bar length. If you are decreasing your end anchorage length, you have to increase the end hook length. What the philosophy is, the end anchorage in any case should have a properly anchored in a zone such that it should develop its tension capacity or what is the sexual force that is acting. But beams, you can have the static point of view also. But when you are talking in terms of the seismic resistance, there is no option. And maybe it can be a bridge of the RCC building. It's a structural action that comes into picture.
And one more thing, sir. In India,
Thank you very much.
the minimum earthquake zone is zone 2. No seismic zone concept is not there in India. That you have to remember. Even previously, zone 1 is there, but now in Indian map, in earthquake map, there is no zone 1. Minimum is zone 2. Hence, you bound to follow this 135 degrees bend.
As rightly said by Sundara Garu, these are the small provisions generally gives you a lot of performance to the structure, sir. Suppose if the client is not interested, or private, especially for the private clients, if he is not interested or not to cope with the earthquake resistant designs, these small provisions of putting some extra minute steel will save you structure a lot from the unhappened unwanted, we can say unexpected or undesigned seismic behavior also. These are the small provisions, even though we call it as seismic or non-seismic designs. Seismic designs is said by Sundarada, it's compulsory now. Even for the private buildings, like very small buildings, putting these small provisions into the practice, you will improve the performance of the structure a lot. That leads to a good engineering practice. Next question, sir.
Sir, question posted by Vidyadhar. Sir, you mentioned that raft beam should be below the slab reinforcement, while for normal slab, top steel reinforcement is above the beam. How
Yeah.
the raft different from normal slab?
Yeah. This problem was occurred in my case itself. I have explained that also. The raft is in a simple sense, it's an inverted floor slab. In the simple sense, it's an inverted floor slab. What is the floor slab that was there, in which the top loading is there coming from the slab top? In the case of a raft, you were the upward soil reaction and also the seepage pressures will be acting on from the bottom of the slab. That is where major principal constituents will be in the top of the plane. And in the case of a slab, the bottom steel will be within the beam top depth, that is within the web member. And the top steel, after your cranking, it will go to the top of the main steel. In the case of a raft slab, the entire structural action is under the reverse direction, and both the steel should be within the beam web of the steel. That is, in the simple sense, it's a inverted flow slab system, in which the both top and the bottom steel of the raft slab should pass into the web of the your beam, and also the bottom layer of the bottom layer of the raft beam should be at the bottom. Above that, the raft slab should be there. For the end anchorage of transverse stresses. And in the case of floor slab, the bottom steel will go into the middle of the web, almost at the top level. Let's say 0.8 depth or 0.7 depth. And the top steel will generally go above the beam steel top after cranking or extra burst.
Can I ask a question, please?
Oh,
Yeah.
One more question, sir. 1 minute. One question by Dr. B.P. Rao in the chart box. The maximum grade of steel for stirrups is Fe415 as per IS 446 2000. But in practice, engineers are using the same grade of steel that was used for main reinforcement. Requested to comment and your advice on this issue.
Yeah, good questions. Good question. The detailed explanation was given in the special publication of IS SP 24 regarding that is pertaining to the IS 456 third version, that is 78 version. Unfortunately, thing is that we didn't have a publication till date in 2024 also, special publication for 2000 year, fourth revision. That is 456 2000 edition. No explanation code is there. Also, our SP16, the SP34 also, they are outdated. Most of the modern day requirements, that is not sufficient. Some of the detailing provisions I want to highlight is we have to insist as a members of ACCA, the Bureau of Indian Standards, let us publish whenever the IS 456 coming, immediately publish the explanatory code and also the SP34 and SP16. See, SP16 was published in 1980 and earlier third version is there in 78. 2 years within gap it has came. But till date, 2000 year, the fourth revision has came. Till date, 24, almost 24 years, we are in a pathetic situation of not having the special publication and also with respect to the explanatory code of the IS code 456 and also the SP34 is also outdated. Also, some of the detailing requirements that was shown the SP34 is not clear also. There is a confusion with respect to the combined footings and all. Which all should be written to our ACE members, to our head centers and all that. This is one my humble request. And regarding coming to the point, The permissible stress in the stirrups can be generally taken similar to yielding of the steel, that is 0.87 Fi. When it is a yielding member, like a hoop tension, subject to hoop tension, it's a pure tension member, that is 0.87 Fi is the criterion, that is the maximum tensile force applying a factor of safety of 15%, 1.15 to the yield stress when it is a hoop tension. But when coming to the diagonal tension crack under the seismic behavior, or the dowel action is considered similar to a gravity loading design, in which the shear stress in the stirrup is considered under the dowel action. The dowel action, the shear capacity of the reinforcement placed into capture, in which the concrete generally will have a shear capacity of 1 or 1.2 Newton per mm square, or the tau c maximum value of 2.8 or 3.2 Newton per mm square. That is a permissible value of this. Similar to that, the earlier third version is limiting that grade of steel for the stirrups limited to Fe 4 and 5. That was clearly mentioned in our SP24, that is explanatory coordinate handbook. That is, the steel, once we are using more than Fe 4 and 5 grade, we should limit the stresses in the stirrups to a stress in the stirrups value to a value of not more than 415 megapascals. Suppose earlier we have no practice of the availability of 415 megapascal steel, only we have the 450 megapascals and lower than that 250 megapascals. Now we have 500, 550, 600 grades of them. And earlier coordinate provision is there with respect to that is pertaining to this limiting of this to 415 megapascals. That is corresponding to the shear capacity of the stirrup in the dowel action. That is the one-way shear, cutting into two pieces, similar to our earlier practice of cutting of bars, where you used to cut the steel bar with some sort of iron wheel, and after that one strip of flat is there. Above that we'll put rebar, and above that we put the sanum, that is the chisel, and after that we'll put one hammer, big hammer. Using that we cut the bars. Similarly, that is a dowel action. Practically, that's a dowel action that is taking place in the RCC beam element or the column element when it is a diagonal shear action is there. For the diagonal shear action, we have to consider the shear capacity of the bar in one-way shear. The one-way shear action generally to being the beam failure is a shear failure is a brittle in nature. We want to eliminate that brittle failure and the catastrophic failures of the shear reinforcement. The code is restricted that value of not more than 450 megapascal. The concept of the code that was clearly mentioned in the ISSP 24. That is the reason for this is to avoid the brittle failure of the nature of the shear failure of the members. The stress in the yield stress of the steel is limited to 450 megapascals. But that is all subject to a research portion, research point of view. We can, I think, if the data is available, we can use that. Earlier, we used to design this stellar spacing based upon our this 0.4 Fi by 0.4 Fi by BSV. BSV equals to that 0.4 Fi is nothing but is the stress corresponding to the permissible stress corresponding to the dowel action of the steel reinforcement. One way we are reducing the stress to 0.4 Fy in the diagonal tension, and the Fy value also we are limiting to 450 megapascals. I think 500 also with a good research we can adapt for higher values also. The basic 0.4 Fy is corresponding to the permissible stress under diagonal tension, that is to one-way shear dowel action. And for the when it is a case of a hoop tension similar to bursting tension, 0.87 Fy, but we are not using that 0.87 Fy. We are using generally 0.4 Fy as a criterion, subject to limiting to Fy value of 450 megapascals. Hope we will have it.
Can I come in, please?
Yes, sir. Yes, sir.
Yes.
If I heard you correctly, you said laps in the column rebars should be welded in a seismic resistant design.
Hmm.
What is the effect of welding on the strength of the rebars?
Fine. Sir. 1 minute, sir. This problem is looked into with respect to the metallurgical phases of the steel that is available in the market. Earlier, the code is also stringent, and the availability of the bars is also not that much of that is a sophisticated one. The earlier bars are with the higher sulfur content that leads to preheating and also there is a degradation of the mechanical properties after the building of the bar. And also the most of the departmental engineers where in those days have the practice of building of the bars, they will be permitting only under the presence of supervision of building of the bars. After that, there is some sort of QC testing also. Whenever only these criterion is satisfied, then they used to allow the building of the rebars. But when coming to the modern TMT bars, they were having very low sulfur content. This low sulfur content will generally allow you a low smoking during the building process, and also the non-necessity of preheating of the bars, and the non-loss of the yield strength of the bar that is there. The primary factor that is to be looked into is the loss of the yield stress of the bar after the building. That is important. We should not lose the yield strength after the building. The build strength should gain the strength of the bar, that is having the tension capacity more than the required capacity. Generally suggested that should be 25% or 30% more than the yield strength of the bar, that is the builded joint. Once this criteria is satisfied, we can allow the building of the bars. But when we are looking into the metallurgical phase of the modern TMT bars, they were superior grades of steel. Building can be possible. When promoting various steel companies also, they were saying that they had the good excellent weldability also. That is one of the best qualities of the steel they were producing. That is one of the marketing strategies. That signifies that these bars can be easily weldable. Now that much of welding allowing of stringent quality control is necessary. But earlier the apprehension and earlier the fear of the welded joints will have a lesser strength, will fail at a stress that must be below the yield stress of the steel. That problems that is not there with the current practices.
Would it not be a better option to use a rebar coupler instead?
Yes, sir. We have the recently we are using two technologies. One is the rebar coupling. Rebar coupling also we have the in situ coupling we are now seeing. That is one of the latest techniques, and also thermite welding. Some of the Malaysian, Southeastern countries they were going with the thermite welding also. Thermite welding with this aluminum powder and thermite welding is also permitted in situ. Southeastern Asian countries are going with that. That is one other option we have. And also we have the latest technology of this rebar coupling sources. But that also requires some sort of QC testing. At least some bars is to be tested for the pull-out test.
Thank you, sir.
Thank you, sir.
Any participants? I request the participants to ask your questions directly. Unmute and ask. If no questions are there, we will conclude the session. Chairman sir, shall we conclude the session?
Yes, sir.
One question posted by Shivaprasad. Could you suggest any latest books on detailing, sir?
Yeah. Yeah, regarding latest books on criterion, like earlier we have the good participation from the academic staff, like we have Essence Sinha, he had given one detailing, and also Taj Steel, they had the one detailing book is there. And now most of the like publishers itself, they are showing not the interest. If you are interested, Taj Steel book is there, and I think some of the foreign codes like New Zealand code is giving much more emphasis on the this detailing projects. If you are interested, I have that copy also. I will share it.
SP 34 is there.
SP 34 is the
SP 34 is given by Bureau of Indian Standards. That is the most standard book. You can download it free of cost from BIS website.
You have the code of practice of 2502 is there, and you have to follow the SP 34 also. Those are the two standards. And for the bridges, you have the IRC 112 is there, and you have the most standard drawings. But one of the unfortunate thing is that even the most standard drawings which was published in 1974, and the IRC 112 has revised with limit data after the 2011 IRC 112 has come, and 2016 there is a revision. Till date, And also 2019, the Ministry of Surface Transport has given to the these as consultants to publish the most standard drawings based upon the limit state. But till date in 2024 also it was not published. That is one of the drawbacks we have. Bridge drawings still we are relying upon the old working stress method, which was published in 1974 itself. Why I am suggesting this New Zealand 4 days? They had their excellent provisions when compared to our ISSP 34 also. Previously, there are some private publications also, like Todd's we have the special publications. I think Essence in also I have the copy. If it is readily available, I'll definitely share to you, sir. I think New Zealand version soft copy is available with me. If it is there, I will share in our WhatsApp group also. And one request to our AS members, for the local centers and the headquarters is, let us insist these basic codes. The Indian standard is lagging behind this publishing of special publication to the IS 446. SP16 also. Some of the provisions in the SP16, now we are using most of them are softwares, but we are relying on the SP16. Most of the codal provisions are not applicable to the SP16 of 1980 version. Even the detailing practice in SP34 is also not clear, especially for the mission foundations and also for the combined footings. They were not clear, sir. What it requires is some sort of colorful 3D presentation of the images. And also I suggest you have some sort of CDs, like colorful CDs of presentation, not a general routine 2D printings in the special publication. Have some sort of videographic presentation illustrations in the code itself. And also the detailing of the members of the code itself. That gives you a lot of presentation when compared to previous SP34 version. That should be insisted to our AS members, the headquarters and the local centers.
Any questions?
Sir, thank
Yes,
you
sir,
very
we are
much, sir.
concluding. Yes, sir.
Could you please share
Yes,
the
please.
names in the chat boxes so that we can download it, we can search in the online or somewhere else?
Yeah, right, sir. Right. Definitely.
Okay, sir. Thank you, sir.
Thanks to Chairman Balan Sundaragaru for his initiation and energetic support in this webinar organization. My sincere thanks to Dr. K.V.Narasimharao garu for his valuable and most practical webinar present preparation and his time to the association and his knowledge sharing to the members. Thanks to the member participants from long distances. Special thanks to our past president, Dr. Ashwath M.U. and senior most engineers participants are there in this webinar. B.S.C. Rao garu and some other participants. My special thanks to ACCA headquarters for his support and encouragement in these webinar organizations. My thanks to all ACCA members, students, faculty, co-engineer friends, managing committee, our member Sairam for his support in this webinar organization. Thank you all. Thank you.
Thank you, sir. Thank you, one and all.
Thank you all.